Our today's topic is separable differential equations. Just like algebraic equations, for example, x squared minus 7x plus 12 equals 0. We can solve this equation by many methods. One can be quadratic formula, can be factorization, or completing squares. Similarly, some differential equations can be solved with more than one methods. Let's start with the separable ones. A separable differential equation has the form like this. You can write a separable differential equation in this form. So we can separate out the x function and the y function with the multiplication in between. Yes, that's very important. With the multiplication in between, not addition or subtraction. Let's take a very simple example. For example, this question, it says solve the given differential equation by separation of variables. So it is given in the question that which method we have to use. Right. Now, first of all, we have to separate the variables. We can send dx on the other side, and we can write it like this. And now we can integrate both sides, and that gives y equals minus 1 by 6 cosine 6x plus a constant. There are two things which are very important to note here. First of all, we can never use dx or dy when they are in 1 over forms. For example, we cannot integrate like this or like this. This is wrong. This can never work. They must be some function. There must be some function dx like this. That's better. That's the correct value. They must be like this. They can never be dx or dy can never be in the denominator when you integrate. You cannot integrate like this. So that is first very important point. Integral of sine 6x, well, you can remember from calculus, you can recall from calculus that it is minus 1 over 6 cosine 6x. We do not add constant of integration, this thing here. This is constant of integration. Well, something is wrong with my touch screen. Maybe it needs calibration. This thing is called constant of integration. We have used this in calculus as well. We did integrate both sides, but we did not add constant of integration on both sides. The reason is, if we will, let's say if we do add constant of integration on both sides, it will be no use. So if we add, let's say, y plus c1 here and minus 1 by 6 cosine 6x plus c2 here. Now we can, because c1 and c2 both are real constants, we can bring them together and they are unknown constants, they are not fixed constants, we can bring them together, cosine 6x, and we can write c2 minus c1, and then we can easily rename them as c. So that's why we do not add constant of integration on both sides, because they can come on one side and become one constant. So we will only add on one side. Let's take another simple example. Right? To separate the functions, variables, first step we need is dy by dx equals minus 2x y square. Now the functions are in multiplied form, 2x and y square. Minus is the minus 1, which can be used with any of them. Now we separate them out, and I will integrate in the same step. Dy over y square equals minus 2x minus 2x dx. As you can see, y square comes down here under dy, and dx goes up and multiplies with 2x. Now we have only y on this side, only x on this side. Okay? Another point to note. Throughout this course, I will keep mentioning most common mistakes. Whenever I say the words most common mistakes, please hear them very carefully. Most common mistakes are the mistakes students do usually, which I have learned from the experience over the years. So here is one most common mistake students do here in this step. For example, they will shift something like this. Dy equals minus 2x y square dx. No, you cannot integrate like this. There is a y square here. There is a y square here. We cannot integrate. It is not equal to minus 2x square by 2y square. No, this is wrong. This is wrong. This one is wrong. We cannot write it like this. That step is wrong. Right. So we cannot do this thing. We cannot integrate like this. It should be completely separation of variables, as the method says, separation of variables. Okay, completely separate. No x in the side of y, no y on the side of x. Well, this integral is minus 1 over y, and this integral is x square by 2 plus a constant. Generally, simplification of the solution is not required in differential equations, but one or two steps would be, of course, very nice. That's more or less aesthetic. So I'll just cancel 2 with 2, and that's our answer. Please note that the formula I have used here to integrate dy over y square is y minus 2 dy, and then y minus 2 plus 1 over minus 2 plus 1, which is y minus 1 over minus 1, and that can be written as minus 1 over y. Right. A very important question would be, how do we know whether the equation is uh, a separable equation or not? How do we know? Is there a formula that tells us? There is no formula that can tell us that the equation is separable. It is only our knowledge of algebra that tells us whether the equation is separable or not. We try certain steps and see if we can separate the variables within the rules and regulations of algebra. That's all we can do. Let's see our next equation, and I would ask you if you can tell me before we start the solution. All right. What is your guess? Is this a separable equation or not? Can I separate x and y on both sides of equality? Can I make it look like some function of x dx and equal to some function of y dy, something like this? Is it possible to take from here to here? Can you give it a try? Pause the video and give it a try. Right. The trick we are going to use here is a very simple formula in algebra which we learn in the very early stages of algebra. Is x power m plus n can be written as x power m multiply x power n. If the base is same, powers are added together. And we are going to reverse this step to separate them out. Once we have this step, e raised power 3x multiply e raised power 2y. Now they are multiplied. Now they can move easily. And we can move them like this. So we will bring so 3x comes down, dx 1 over e raised power x 3x dx equals 1 over e power 2y is up, e raised power 2y dy. Did I make a mistake in this step? What do you think? Am I doing all right? Is there any mistake? Can I integrate them like this? Well, if you have said no, then you are right. I cannot integrate them like this. I have made a mistake. Dx and dy, if you remember, I said a couple of minutes ago, they cannot be in the denominators. They must be in the numerator for us to be able to integrate. So this step is incorrect. Let's try it again. I'll leave this step there for your record, and let's try the step again. Okay. Dx will have to go up. It means e raised power 2y should come down. So this will be e raised power 2y over, dy over e raised power 2y. dy over e raised power 2y equals e power 3x dx. This is correct. Okay. Dy and dx should always be in the numerator, never in the denominator. Okay. Right, this can be written as e raised power minus 2y dy. This can come up and become minus integral. I'll write this again just for similarity. Now we have minus 1 by 2 e raised power minus 2y, 1 by 3 e raised power 3x plus c. The formula here is very simple. Integral e raised power ax dx equals 1 over a e power ax. I'll write it down here. Let us try a slightly different question. It is question number 18. dn by dt plus n equals nt e power t plus 2. Of course, there is no harm. Pause the video and try the question before I do it. That will give you very good experience on how things work. So again, what do you think? Do you think it's a separable question? Can you separate them out in the form of some function of t and a dt and equals some function of n and a dn? So that's what we are looking for. Can we do that? Let's see. There are two possible approaches here. One is we can divide the whole equation by n, or we can send this n to the other side. I'll take this approach here. dn by dt equals nt e power t plus 2 minus n. Now clearly we can take this n common, okay, because we cannot send this dt there yet because they are mixed, n and t mixed. So sending dt over there will not solve our problem. As I have said earlier, we must separate the variables. No n on t side, no t on n side. So take the n common, t e power t plus 2 minus 1. Yes, this should be 1, not 0. Remember that. Now this n is multiplied with the expression in the bracket. We can move this n down here. Okay? Multiplied here, divide on this side, equals t e power t plus 2 minus 1. Keep the bracket on because dt is multiplied with both of them outside here. I'm leaving this space for another approach, so I'll come back. dn over n, that's clearly log of n. I'll not put absolute values for now. I'll consider that n is positive. On this side, yeah, okay, we integrate. We'll make two integrals, t e raised to power t plus 2 minus integral dt. This one is by parts formula. Yes, I missed to write dt here. Must write dt. Yes, something. dt minus dt. This is by parts formula. So we write first function as it is, integral of second minus integral of second derivative of t is 1. So it comes down to this minus t plus c. And in the second round, we get our answer. I hope you remember the by parts formula here. This is by parts. Right. Let's see one more approach to the same question. What if I divide the whole equation by n? 1 over n. Show you the equation. dn over dt plus 1 equals t e raised to power t plus 2. So we divide 1 by n over here. When we divide 1 by n here, it becomes 1. And when we divide n here, n and n cancels. Now, can I write from this step, is it possible that I can write 1 over n dn plus 1 equals t e raised to power t plus 2 dt? What do you think? Is this step correct? What is wrong with this step? Is there something wrong with this step? it is wrong, of course. And what is wrong with it? We multiplied dt across. Okay, we multiply dt here, so it vanishes from here. We did not multiply dt here. That's what is wrong with it. So the correct step from here would be, 1 over n dn plus dt equals t e raised power t plus 2 dt. Or first send 1 on that side and then shift dt. That will give you exactly the same equation as this one or this one. If you send dt on that side, you get exactly the same equation. So 1 over n dn equals t e raised power t plus 2 dt minus dt, and you integrate, and that is exactly the same expression. Right. Well, it looks like that it is not separable because there are all the plus and minus in between. So we cannot directly separate the variables because of these plus and minus. But there are lots of tricks in the algebra's sleeve, and one of them is factorization. How about factorization? dy by dx, x common, y plus 3, minus 1 common, y plus 3. Again, x common, y minus 2, 4 common, y minus 2. dy by dx, y plus 3 common from this one, and this one. Take y plus 3 common, and the rest is x minus 1. Similarly, y minus 2 common, and the rest of it is x plus 4. Now clearly they are multiplied. As you can see, y plus 3 is multiplied with x minus 1, y minus 2 is multiplied with x plus 4. Now we can easily separate them, but remember, dy should stay in the numerator up and dx should go up. So y will move here. Y minus 2 over y plus 3, the one which is up on this side will become down, divide on this side. The one which is divide on this side will go multiply, go up on that side. Equals x minus 1 over, and this integration is also very interesting. You can do this integration by starting with the long division, because the power of the polynomial is same in the numerator and in the denominator, and this rule is taught in partial fractions, that if the power of the polynomial is same, then you must reduce it first, okay, by long division maybe, and that is, oops, used same. So this means, so this gives, and similarly, right, from these we can write 1 minus 5 over y plus 3 dy, 1 minus 5 over x plus 4 dx. And now we can easily separate these integrals into two. This will be dy minus 5 times integral 1 over y plus 3 dy, integral dx minus 5 times 1 over integral x plus 4 dx, y minus 5 times log of y plus 3, x minus 5 times log of x plus 4 plus 6.